So in the last video, I ended by talking about how we can phrase reordering the operations in our producer and consumer loop as a synchronous data flow problem where we fill in parameters, rates, and delays for these two scheduling functions. So let's take a look at how that'd be done. So the goal is we want to make things happen as soon as possible. So we want to minimize the rates at which statements execute, and we want to minimize their delays, subject to the constraint that an iteration of the consumer loop cannot start until the producer of the last element of the memory needed by CX has finished. And there's also some boring constraints that normalize so that things don't start before time equal to 0 and so on. But basically, what the thing is, we want to minimize rates and delays. Oh, excuse me. Subject to every single operation happening after all of the data it needs has been produced. So using synchronous data flow forms, or scheduling functions, this really boils down to the rate of the consumer times x plus the delay on the consumer has got to be greater than or equal to the rate on the producer times x over 2 plus the delay on the producer. And actually, this is a nonlinear problem, right? Because really, there's an implicit quantifier out here that's saying for all x, we've got to have that this inequality is true. So we've got to somehow get rid of these x's. And the way we're going to do that is by what's called rate matching. So we're just going to isolate these two terms, and we're going to say, you know what? We're just going to set the rates so that these terms are always equal. So we're going to reduce this to the problem that QC times x has got to be equal to QP times x over 2. So notice, here we have an inequality, here we have an equality. And this really just boils down to 2QC times x equals QP times x, which boils down to 2QC equals QP, which boils down to QC equals 1 and QP equals 2, or that's one possible answer with small values of QC and QP. So now that we've got the Q values, we can plug them back in, and we get 1 times x, plus dc is greater than or equal to 2 times x over 2 plus dp. So now we can just reduce this, so this 2 times x over 2 and this 1 times x are going to cancel, and we just get that dc is greater than or equal to dp. And so we get the schedule for the producer is 2 times x, and the schedule for the consumer is 1 times x. And this actually generalizes well to multiple dimensions. So if you think of the inner loops as data flow units in a loop nest, we can start by scheduling the outer loop as if the inner loop is going to be executed in a single instant by a super powerful functional unit. And then once we've scheduled the outer loops, we can remember that the inner loops, or that the bodies of the outer loops actually contain more loops, and go inside and recursively work our way through the loops in the loop nest, doing a synchronous data flow schedule for each level. And by repeating that recursively, we can build a schedule for complex multidimensional loop nests. So for example, if we have something like this, which is a stencil in 2 dimensions, it's a 2x2 stencil where we write values to an image, and then we read out this 2x2 stencil with the top left corner at nm. And we can start by scheduling the outer loops first. So we basically do for I in 0 to 4, we produce a row of image, and then for m in 0 to 3, we can consume 2 consecutive rows of the image. So we can boil this down to a new schedule for the outer loops, which is for y in 0 to 4, produce image, and if y is greater than 0, consume y minus 1 and y. And then once we schedule the inner loops, we get something that looks like this. The final loop nest is for y in 0 to 4, for x in 0 to 4, no matter what, set the next pixel of the image. And then if x and y are both greater than 0, do one of the output stencils of the 2x2 stencil in the original consumer loop nest. It turns out there's also a complication in hardware, which is you don't just want to minimize memory size, you actually want to maximize memory bandwidth, which means banking or partitioning your memory to allow a large number of simultaneous memory accesses. And that's a complication I'm not going to talk about in this video series, but it's something that I'm going to get to in other videos, because it's usually the number one thing that determines performance. So getting minimized memory size is awesome, but maximizing memory bandwidth, especially in memory-bound image processing operations, is absolutely crucial as well. And so it's something we'll talk about in later videos. All right, so if you have a comment, leave a comment down below and let me know what you'd like to hear more of. But for now, I'll see you in the next video.